Okay, welcome everybody. It's a pleasure to have today Casper van Elteren. He's a local PhD student with Rick, and we're all very curious to hear what he has to say about information flows in complex network, complex systems. Sorry. So take it away, Casper.
Yeah. Well, thanks for the kind introduction. So yeah, to re-emphasize, my name is Casper van Elteren. I've been a PhD student for about 1.5 years now. And today I will introduce the topic of information flows in complex systems. And my slides will, as always, be available on my websites, but they will come up again at the end of the talk, so don't have to write it down right now. Roughly speaking, the talk will consist of 2 parts. So I'll first talk a bit, due to the interdisciplinary nature of everybody attending this talk, about what complex systems are, and also specifically how I define complex systems to be. And then I will slowly transition into information flows and talk about information theory. The whole content will be more high-flying than last week, where Velimir had a really good and extensive introduction to information and what information exactly is. And then in the second part of the talk, I will give some examples of how information flows can be used to study complex systems and how we can use it to get some new understanding of what you can do with complex systems at all. In particular, I will focus on driver node identification and tipping point analysis. And this part is a bit more recent work, so it will be a little bit thinner than the first part. So yeah, first, to have like a conceptual introduction of what complex systems are. What we know is that they exist everywhere in nature, and they also exist at all different types of scales. So we can talk about, for instance, subatomic particles that together interact to bring forth the periodic table. And even higher level, these atomic particles, they can bind together to form complex protein complexes. So this, for example, is a study that was recently published on how a ribosome actually produces the spike protein from the SARS-CoV-2 virus. And then at a higher level, these protein complexes can bind together to form things like cells and how cellular processes operate. And these cells bind together in networks to do even more larger things. So this, for example, is the zebrafish brain that using optical imaging, you can actually map large-scale brain dynamics over time. And this is an animation I made based on the COVID data from the Dutch government. So also at system level, we can see large-scale system level, we can see complex interactions happening. And then possibly maybe the largest scale that's relevant for humans is the planetary scale, where we have climate systems interacting over time. So this hand-wavy introduction, if you look at it together, we have all these systems existing at different scales. And each one of them is considered to be some form of complex systems, and they can also interact across different scales. And understanding these systems is vital for everything we know about life in the universe and everything else. And this is also highlighted by the late Stephen Hawking, that said in the interview in the early 2000s that understanding complex systems is essentially vital problem for the 21st century. So can we do anything better than just this hand waviness? Well, luckily, the term complex system is used by many different fields of study. So they all fall under this banner, umbrella term of complex systems. Disciplines ranging from physics to biochemistry to psychology. Economics can also be considered to be fall under this. And they all sort of have their separate definition of what a complex system is, unfortunately. So till date, there's not really a generally agreed upon term or thing that we call a complex system. And there's this excellent paper by Lederman that sort of goes into this discussion on what parts can be considered a complex system. Generally speaking, people do agree on certain parts, and those can be decomposed into 4 properties. We basically always consider a complex system to consist of many parts. And these parts are not just a mere heap of things. No, they actually interact in a particular way. And these interactions generally create some form of pattern through self-organization, meaning that there's not a central control unit that sort of dictates what the system is doing, but it's through local interactions that these patterns are formed. And lastly, what is sometimes maybe forgotten in analysis is that these systems also have memory. And then I want to make the distinction here that there's a complex system and a complicated system, and those things are not necessarily the same. So a complicated system also consists of many parts and have interactions, But the difference between a complex system and complicated system is that a complicated system is highly predictable. So a good example would be, for instance, something like a watch. A watch consists of many cogs, they interact together, but the output of this system is highly predictable. It tells time. And lastly, what's also very important with these systems is that there's this relationship between parts of the system that generate this something else at the system level. And this tension between how these parts generate these properties is what I would like to understand. So I would like to now take a bit slide to go a bit deeper into what I exactly mean with this, so that we're all on the same page on what I mean with complex systems. So I always like to give this example of the game of life. For those who are not familiar, it's basically a chessboard where you have cells that can be in two states, either alive or dead, and they have 4 simple rules. If you're alive and you have less than 2 cells that are active, the next time step of this system, you die. If you have more than 3 cells, you also die. And if you exactly 2 neighbors that are alive, you remain alive in the next time step. And similarly, if you're dead, you could have the situation where you have 3 neighbors that are around you that are alive, I believe. And then you turn into becoming alive. And this simple system already can generate really complicated patterns. So these are a few examples where you start with a particular configuration, and as you simulate the system over time, you can get these things called gliders here on the sides, but also these things called oscillators. And there's many other different patterns that also are not necessarily temporally stable. And if you put this on a grid, you can actually get quite complicated patterns happening. So just to sort of unpack what we see here is that just essentially 3 salient things happening. We have these blobs here at the side that are doing something. And then we have these 2 cross beams that is, in the end generate this ship that flies off into the distance. And what is interesting about this system is that every part that you see on the screen here contributes to in some way to generating this large glider here. So even at these sides, there's these local interactions happening that in the end contribute to this stream being formed and then this ship being constructed. And so what's interesting about the game of life, what this tells us that even with simple deterministic rules, it's very hard to predict, just giving those rules, what a system will do as it evolves over time. And this is quite characteristics for many complex systems, namely that they're really generally difficult to analyze. And in this talk, I will mainly focus on 3 different disciplines. I will use network science and information theory and nonlinear dynamics to sort of get to another way of understanding complex systems. Let's see. Yeah, so what do I exactly mean with a complex system? So for me, a complex system is a set of particles that have an interaction structure indicated by these blue blobs here, the particles, and the edges being indicated by these gray connections. And these particles interact in some meaningful way. There's some function that dictates their dynamics. And then together, they generate something that we call emergent properties. So it's similar to what we know about the brain, that we have these local neural interactions, and their togetherness generate what we know as consciousness at the system level. So how are complex systems traditionally studied? Well, I think we can have sort of 4 different ways of people traditionally using this concept to study complex systems. The first one is basically, as I just depicted, you have a network structure and you have some dynamics that evolves over time. And this is what I would call the happy case, because we have a lot of information available about this system and we can study this. Unfortunately, it becomes a bit difficult in practice because this function may prove difficult to analyze in practice. So it can either be that we only have a description that's locally correct, but not globally, or if you have a global, let's say, global equation, it could be difficult to form a solution for this. And it gets even worse. We can also have situations where we only have a known dynamic, but not a known interaction structure. And how I like to think about this case is, for instance, with the SRR dynamics. So for those who are not familiar, basically what you have there is that people generally disregard how people socially interact, and they assume some stochastic nature under the assumption of homogeneous mixing. Everybody in the population can interact with anybody else, and there's no regard on how this interaction exactly takes place. But still, using these SRR dynamics, we can, to some degree of accuracy, predict how epidemic will evolve over time. This is still a fairly good case to be in. And then it can even get even worse, is that where we have a system where we can sample it over time, we have observations, but we don't really know how the interactions are embodied, and we don't know what the dynamics are. So this case would be something like cognition, as I highlighted earlier, where we do have access to the system. We can sample it, we can record EEG, we can record micro recordings of electrons of neurons, but we don't really know how consciousness is generated. And then moving a bit up in a more suitable case is where we have a network available to us, and we have observations from the system, but we don't really know what the dynamics are. And this case is probably the most prevalent nowadays because we have a lot of tools available to us to map out network structures like protein-protein interactions. And we have a lot of observations of the systems, concentration gradients, or how many times people interact with each other, but we don't necessarily can formulate that in a mathematical equation. Yeah, so for instance, with social networks, with the advent of social networks, we can probe Facebook for mapping out the social network, who talks to who, but we don't have an equation that describes the social dynamics between these people, or at least not to my knowledge. And this is actually the case I'll be focusing on today, where we're wondering, given this network structure and these observations, can we say something from this network structure about how important a node is in this system? Yes. So it naturally leads to this question of, does structural importance imply dynamical importance? And how people traditionally do this is they go to network science and they apply these things called centrality metrics that take a structural feature and assign an importance score based on that structural feature. So the most famous one is degree centrality, where the importance score is proportional to how many connections you have. So this is a traditional kite graph where I made the node sizes proportional to how important that node is according to the degree centrality. And this center one would then be considered the most important node. But it already highlights a big problem because we don't have just degree centrality being important. We have many different forms of centrality metrics. These are just a subset that you can use, which are the most traditional ones. For instance, betweenness centrality takes into account how many times a node acts as the shortest path between other nodes. And if we take this to be important, a high importance score for a particular node, then we identify this orange node here to be the most important node, but this central one is not considered to be that important. From a graph theoretical perspective, all of these centrality metrics essentially map out the walk structure of a graph. And from a complex science perspective, we can say they implicitly assume a dynamic. So in this case above here, but between the centrality, if we assume that structure to some extent implies a dynamic importance, then we also by proxy assume that the dynamics of this system is governed by shortest path dynamics. And that's quite crucial to understand, because when people apply centrality metrics to understand, let's say, disease spreading, they often come up with a different centrality metric that behind the scenes implicitly also assumes a dynamic. And when the dynamic doesn't match the system you're looking at, you can actually get different claims about what node's most important. So we get from this basically a question, okay, but what dynamic, how does the structure relate still to this dynamic? We need something to say about this dynamic. Well, people have looked at this. So there was this nice paper by Harouche in 2017 that they published in Nature Physics, where they essentially kept the network structure fixed. So this circle, unfortunately, this is the original graph, but this really shows a network. And they varied the dynamics on this network. And they used some arbitrary equations that they got from popular science articles, where it's genetically based or epidemic based, biochemical or ecological. And as you go from left to right, what should be quite apparent is that these red dots change. And these red dots indicate how important this node was. And they use this flow metric. They literally call it information flow, but it will be different from the information flow I'll be talking about in a bit. And it takes basically the input to a node and the output to a node weighted by this omega factor. And this omega factor was embodying some property of this dynamical rule that they had in place. But this was a very nice study that essentially answered the question. It depends on the dynamic of the network and on how structure implies how important that node is. But unfortunately, in the original case that we were looking at, this requires full, complete knowledge of the system. So we both need to know the structure as well as the dynamics to generate a predictor for the outcome of what's dynamically important. So we go back to this question, does structural importance imply dynamical importance? Well, it depends, because if the two interact, then you can design a centrality metric that would actually generate a good predictor. But if you're not sure, then it could generate wildly different claims. So we're still left with this problem. We have a system that we know the structure of, and we have maybe some observations, but we don't really know what the dynamics are of this system. And we want to say something about this. And if we replace it with some arbitrary function that these particles interact with, we're back in this happy case, but we can actually generate wrong estimates. Yeah, so one possible way to deal with this situation would be to use information theory, because it can infer certain properties based on observations alone. So that's where we come to information flows. But I would like to take some time now first to talk about what information is, so that we're all on the same page of what information is. Because colloquially speaking, information is the more information you have, the more knowledge you have about something. And in information theory, it's a slightly different concept. So the traditional example that people always use is, imagine you have a coin flip, where you want to determine the outcome of this coin flip. So assume we have a fair coin. There's a 50-50 chance that it will be heads or tails. And so how information theory considers information is saying, we want to know the uncertainty of the outcome of this experiment. And the uncertainty in this experiment would be exactly one question you can ask, namely, is it heads or is it tails? It's the same question, but inverted. So the base unit of informational entropy is basically how much uncertainty is there in the outcome of an experiment. So for a fair coin, we can quantify this, and we're in the center. So this unbiased coin exactly gives one bit of information, one question we can ask. But if the coin is unfair, we actually get differential information. So this uncertainty principle is encapsulated by the informational entropy, h of x, where x is the random variable that's the coin flip. And the number of bits we can quantify actually tells us about how biased the coin is. So if we do a bunch of experiments and we end up with zero entropy, we know that's a super biased coin. And how I like to think of information theory in terms of complex systems is that it's actually a source of how much mechanism there is in the system. So imagine this case where we have a 50-50 distribution. It's completely random. So basically the universe tells us there's no mechanism here. But at the edges, we have a completely biased coin. And that can only be the case when, well, unless we're very unlucky with the samples we draw, but it can only happen in the case where a coin is maybe weighted on one side or very folded like a taco, that it only ends up on one side of the coin. So the amount of information content, the amount of uncertainty tells us a bit about what is generating this process. And so this thing of entropy, we can actually extend. So we have entropy indicating the uncertainty we have about the outcome of a process. And we can go further. We can say, actually, well, how much information do I gain if I know the outcome of another variable? And this is what is encapsulated in mutual information, which is basically the reduction in uncertainty of a random variable, given that you know the outcome of another random variable. And this concept, we're going to apply to deduce information flows, because if you're not familiar with mutual information, this is essentially a nonlinear correlation function. And I will also talk a bit about causation, because correlation does not imply causation. So information flow in a nutshell is this. So imagine I have a system vector, some particles that I measured over time, and the amount of information that the system has can be encapsulated in the uncertainty of the system. So there's some state distribution that the system has. It can go to different states over time. And the amount of information that I have is sort of symbolized here with the amount of orange I have. And then in terms of information flow, what we can use is this concept of mutual information, but time shifted over time shifted. So we can go one time step back and say, how much of the information does a singular particle have about the future state? And as it turns out, this process is not equal. So some nodes have more information about the future state than others. So what we can do is write down the conditional entropy of the node one time step before this. How much is this reduced? Reduces the knowing the outcome of this variable reduces my uncertainty about the future state. And if we do this for a bunch of time steps, we can have the flow of information backwards in time, how it decays as a function of how much it knows about the system in the future. And just to hammer this down, I have this toy example here. So this system consists of 4 nodes. There's one driver node here that has 2 downstream nodes, and one node here that has 1 downstream node to 2. The dynamic of the simple is quite simple. So this node has a 50-50 coin flip. It updates its state with 50-50 probability. Each node can assume either 0 or 1 state. And all the other nodes, so 1, 3, and 2, they copy the state of their predecessor. So 3 copies the state of 0, 1 copies the state of 0, and 2 copies the state of 1. And if you use this mutual information time shifted over time, you get these information decay curves, as I just showed conceptually. And what is quite apparent here is that the information decay curves are different. So the black one corresponds to the black node here, the 0 case, and it loses its information the slowest over time. So that means that if I go 3 times back, the node that gives me the most information of the future future state of the system is node 0, which corresponds nice, intuitively speaking, to this causal graph we have. But then the note on causation that I have to give right now is that information flow can be confounded. So we have information flow being essentially a sum of both a causal flow as well as a correlational flow. And where do we see this back in? Well, we see this kind of with 3 and 1. If you compare the information content that they have over time, 3 has no downstream nodes, so it has no causal effect in this system. So the information decay it has is quite similar to 1, but 1 at least has a downstream node it can reach and it can influence. So 3 shouldn't have that high of an information decay curve as 1 has, because it has no causal effect. So the problem we're faced with if you use information flows in this context where you only use 1 node as a proxy for how a state will be in the future, we can only be sure about 1 node in particular, namely the one that shares the most information over time. But given that you have a system where you measure all of the output states, so we don't necessarily know the structure, but we know at least that we know there's no confounding happening in the system. The one that has the slowest decay over time will be the one that's most causal. And it would always be the one that's driving the system state. Yeah, so just as a quick summary, information flows basically is a statistical coherence between 2 variables where we want to know the reduction of uncertainty given that we know the outcome of a variable in the past. And how I do this is with time-shifted mutual information, where I only look at 1 singular node. And the one that maximizes this quantity will be the one that drives the system over time. Yeah, so this concept of information flow is not new. Rick actually looked at this quite early on, like nearly 8 years ago, by using this concept of information dissipation length, where it's basically the half-time of this information decay curves. And he looked at how degree varies with the information content according to this measure. And what he showed is that as the degree increases, the decay rate of this information curve is lower and actually diminishes to 0 for higher degree nodes. So this nicely shows that the information content does not necessarily scale monotonically with the structural features encapsulated by the degree here. This was done with a kinetic Ising model on infinity-sized networks, and so there were assumptions on structure. In particular, there's no local feedback loops. The graphs were all locally tree-like, and there was no causal validation. So this only showed that the information content varied, but we can't really necessarily infer easily from this that which one is actually driving the system. Right, so this is essentially where I came in to extend this work a bit further and to actually take into account graphs that would have local feedback loops, because in complex systems, depending on how you define them, we actually see them quite a lot. Feedback is quite an important property to also generate these things like memory. So we start still with the same issue, the structural importance imply causal importance. And the goal was basically to identify the most causal node using observations alone. And I generated this new metric, which essentially is just the integral or the area on the curve from this time shifted mutual information. And the driver node would be the one that maximizes this quantity. So how did we do this? So going back to this original problem, we have a known network structure maybe and some observation of the systems. And what we essentially did was we faked observations by assuming some dynamic, which made us back into this happy case. And then we only took the observations from the system to estimate driver nodes based on these information quantities. And for people in the know, I won't go into this today. I used also a kinetic Ising model for this. But the output of this, the estimates that are generated were not based on any of the knowledge of the system. They're only based on probability distributions, which could be generated by any form of dynamics. And then it's important to also know that we do assume there's no confounding in the system happening, meaning that we measure all the variables that generate the system dynamics. Right. Yeah, so really hammer this down. So there's no assumptions on structure and there's no assumption on the type of dynamics. We only use observations, and we validate this metric with causal interventions. Right. Yeah. So the output of this study was quite nice. I showed it now a very conceptual toy example. This is the same kite graph I showed before, where each of these centrality metrics generate a different node that is deemed to be most important. So we take those as driver node inferred from the structural properties of the system. And then we use different forms of causal interventions. In the literature, they're called hard interventions when you pin a node state, and soft interventions when you bias a probability distribution. I will go more into this in the next slide, but just to show what you see here is that the causal flows actually change as a function of how hard you intervene on the system. So that's similar to if you're a neuroscientist and you want to understand the functioning of a particular neural population, what is quite nice nowadays is you can use optical genetics to actually turn off and on genes. And this is a very binary state that you can have. And this binary flipping would be considered something in the hard case. And if you want to understand what this system is doing, we actually see that our mutual information metrics is perfectly predictable for the soft intervention case, but not for the hard intervention case. So what do I mean with this? So imagine you have some system indicated by this star graph here, and this is the system response over time, so the average magnetization for the kinetic Ising model. And this is the state of this node in the center here, this zero node. So this is the probability distribution of it. It's nicely-ish 50-50 distributed. And a soft intervention would be where I slightly change the node distribution of this node in the center here. And what we observe is that the system response is virtually unchanged. So they look just by eye virtually the same. Also, it's confirmed by that the probability distribution of this node is virtually the same. But what is interesting, when you do a hard intervention, when you essentially set the node state to either 0 or 1, the output of the system changes dramatically. So if you want to generate hypotheses on how the system operates in a natural case, this will possibly lead to wrong interpretations of what the system is doing, because the system is flipping from stable to stable period with some unstable periods in between. And this disappears when you have a hard intervention. So in this case, this is actually wanted. Like, we want soft interventions because then we understand what the system is doing. And with hard interventions, we observe different causal flows. Yeah, so of course, I didn't just use one single toy example. We used a bunch of different generated graphs. So this is a really complicated figure to just take in. So let's slowly go into it. The take-home message is basically this, is that if you compare the integrated mutual information, so just the informational estimates that predict the driver nodes, the yellower it is, the better it is at predicting the ground truth driver node based on these interventions. And generally speaking, these centrality metrics indicated by these columns here are worse at this. But interestingly enough, they become predictive for these hard interventions all the way at the end. So we come to the same conclusion, is that essentially if you use an informational metric, we can derive what the driver node is in the cases where we have these unperturbed dynamics, as I showed in the previous slide. Yeah, this is also a similar slide. So we also use the real world system. This is a system based on psychosymptoms that we obtained from Pascal Fried. Above here are centrality metrics we used before on this graph. And we see that for degree centrality, for instance, depression is being identified as the most important node, similar for closeness and eigenvector. But then for betweenness, we see how dislike is being identified as the most important node. But importantly, if you look at low causal interventions, we see that SAD is the most causal node. And for hard intervention, it's dislike. And integrated mutual information matches quite nicely with the soft intervention case. Oddly enough, also for all the nodes in the system. So if you compare these ones, for instance, it looks quite similar. But again, we can't really infer something from that directly. It's at least something interesting to see. Yeah, so I just wanted to stop here that maybe people have questions. There's more details in the paper. I'm sort of going through this in a high-flying way. So I would like to open the floor a bit for people to have questions on this procedure. If not, I will just continue. I don't see Zoom, so Bart maybe.
I'm not seeing any questions now.
Okay.
You want to just unmute if you want a question, but otherwise we can continue, I guess.
Okay, well then we'll continue. So essentially the next part of the work I've been working on is extending this concept of using driver node identification, but then on a causal relevant feature. And particularly, we're interested in tipping points. So just as a refresher, everybody watches the news. We all know that climate change is happening. The tipping point is essentially a rapid shift between one regime of a system to the next. So here we have an energy landscape depicted as this nice like wavy thing. And we have time depicted in the z direction. And we started out here, and then the system moved over this energy landscape. And currently we're at this state where we can go to this very stable hothouse Earth, yeah, it's attractor, or we can go to the stabilized Earth. And this rapid shift is what I want to understand. How can we study this from an information theory perspective? So in the kinetic Ising model, as I showed with these intervention sizes, what we see for finite systems is that these systems can switch between a stable period here to this rapid unstable period to another stable period here. These things we call tipping points. They're technically, I think, metastable points, but it depends a bit on which literature you're reading. These are also considered tipping points. And these things are stable regimes, I call them for now. And what I did was essentially the same procedure as I did before, where I wanted to see how the information flow content differs from this part to this unstable regime. So as a function of how far I am away from this tipping point, so we can quantify some distance from here to maybe this part or to that part, as a function of how far away I am. So here I'm in the stable regime, very far away from this tipping point. And the information content flow looks like this. Graphically, that's depicted like this. So I had another toy example here where the size of the nodes are proportional to the area under the curves, the integrated mutual information. And far away from the tipping point, we see that most of the important nodes are on the periphery. They have low degree, basically. And as you move closer and closer to the tipping point, what you see is happening graphically, that the information content shifts from low degree nodes to high degree nodes. So here, if you walk from this graph to this graph, this is still virtually the same, but slowly but surely, these nodes here with higher degree, indicated by white and the salmon color, they start to get up on top. So the information content, the information flows, depending on where you are in this dynamical landscape, it can differ, and yeah, they can be used what we call information cascades. So what we believe is happening is that the energy landscape is being changed by these high variable nodes. So there's these high variable nodes that recruit more stable nodes to flip. And then at some point when it becomes really unstable, these higher degree nodes are being recruited. This is a double slide, I think. Yeah, I extended this even further. Again, this is a toy example. So does this hold for other types of complex systems with other network structures? Well, here I basically tested, I don't know how many exactly. I think it was like 100 or so, each consisting of 100 nodes. And the curves you see here are the cumulative integrated mutual information as a function of the distance, tipping distance. And each color is averaged by degree. So basically what you see is that there's a differential happening, right? You see that some of them flip very close to the tipping point, like this black one, but this purple one flips earlier and this red one already starts flipping very far away. And so what I kind of did was I focused on this point where the second derivative is maximal, and I then quantified it according to the degree. So here we're very far away from the tipping point, and this, yeah, I'm not sure what you call this point, but let's call it the bend point. It's technically not correct, but let's call it the bend point. This bending point, it occurs earlier for low degrees, indicated here by red, and then slowly moves up the scale when with degree. As you go closer to the tipping point, this bending point occurs later. The higher degree, the later it occurs. Yes. Yeah, so as a conclusion / outlook, complex systems are, I showed you that complex systems are difficult to analyze. They have these many interactions. Information theory can form a nice way of analyzing these systems because you can do it based on observations alone. There's of course all kinds of restrictions you have, which I didn't go into in this talk. I showed you the form and function are not necessarily the same, and they interact non-trivially. And tipping points can form an interesting way to see them from an information theory perspective. And I'm not actually sure how good I'm on the time, so I'm going to quickly put in the slide of self-promotion. Basically, in support of this study, I've also made this toolbox that's available on my website on GitHub. And I'm looking for people to also start contributing to this. It's pretty fast, pretty reliable, and you can put it in any type of dynamic you want, any type of graph system you want, and it produces this nice overview. So I would be happy to open up the floor now for people to ask me questions or thoughts and experiences. And thank you for your attention.
Right, thanks a lot, Casper. I would say mute and clap a little bit, or throw your digital claps in. All right, and if we have any questions. I see a question by Peter.
Hi, yeah, Casper, a very interesting talk indeed. I mean, I've seen this from afar, and I think it's very interesting and very exciting. Yeah, I had a question, which is possibly a basic one, referring also to your last part. So in general, if you think about statistical physics and you think about tipping points or phase transitions, people look at fluctuations and about if there are large fluctuations in the systems, then you are about to cross the phase transition. So the question is, how does this information theory and all these measures connect to that point of view? This is more the classical point of view, I think.
Yeah, that's a good question. So I think so people have used information theory to sort of look at these this critical slowing down, where you actually try to predict when a system is going to change into the next state. This is slightly different, I think, because essentially what is happening here is that because it's a kinetic Ising model and it's undirected graphs, the relation works both ways. So imagine if I have a star graph with infinite amount of leaves, then this center node is highly stable because it operates through this majority voting, basically. And what is happening here is that as it moves closer to this tipping point, the average magnetization of its neighbors becomes more unstable. It comes closer to zero energy, basically. So in that sense, it's related to, if you were to look at a system that shows critical slowing down, this higher degree node would be more likely to be recruited in contributing to the dynamics. Whereas what is happening here is that this center node is just super stable. It gets like, I don't know, minus 100 energy every time. And then some of the nodes will start flipping, but it doesn't really contribute to a large change in system dynamics. So here, for example, most of these fluctuations you see here are just leaf nodes flipping somewhere. nodes with low degree. Whereas what is happening here is that actually the center node has to flip to change the magnetization into a different regime. I'm not sure if this answers your question, but this is sort of the difference in interpretation, I think, that we apply here. So
Okay.
and what is nice about this is that you can do this based on observations. So if you have, I don't know, a climate system where it may be very hard to write down an equation, you can still apply these methods in theory. Whereas it would be harder to say, like, how does a tiny variance in my equation change the outcome?
Yeah. Okay. I mean, I guess I mean, it's an unsolved, maybe an unsolved problem at the moment.
Yeah.
I mean, it's not entirely clear to me how this relates to that, but maybe I have to study a little bit harder. Thanks for the answer, Andy.
I see another raised hand by another Peter.
Thank you for the interesting presentation. I'm just curious, your examples and your simulations all are based on Ising models. Now, from the background of my institute, we are more interested in information spread in the gossiping sense, or people convincing each other about opinions. How far is that different from the Ising mechanics, and have you run similar experiments for models of interaction which are closer to what's happening within these social networks?
Yeah, so that's also an interesting question. So what I know is that this Ising model has also been extended to different fields. So neuroscience uses them, for instance, to study neural behavior, but also voting dynamics has been used as a proxy for the Ising model. I'm not too familiar exactly how they changed the model, but what is important about the methods described here is that we use systems that are ergodic. So as long as the equations you're using satisfy these properties, we believe, but we don't know for sure, that these results would translate well. So in terms of the voting dynamics, if you have a non-ergodic system, there's other issues you have to solve here, but those are generally also very difficult to study. I'm not sure if that answers your questions as well, but at least I'm trying to highlight is that if you have a voting dynamic that is ergodic, you could apply these methods.
So maybe these social networks are not stochastic enough. Okay.
Yeah, this is another thing I think I didn't have time to get into, because this original definition I gave with the complex systems, of course, in real world systems, we have time varying dependencies between the particles you're looking at. And this is another problem we're trying to get into, but with the current studies, we only looked at static networks.
Okay, thanks.
Are you, I had a small question actually. Are you also assuming your dynamics is time reversible, or in that sense satisfies detailed balance? Something like that?
Yeah, in the case of the Ising model, they do. Yeah.
Okay. I saw other question by Clelia first. Oh, she removed her hand. Then Alexandra.
I think Clelia was first, but she's not. Clelia.
Yes, I can ask it now, or yeah. So I was trying to compile another question, that's why. So I had a maybe very simple question actually. The mutual information, what you call mutual information flow, I think it is predictive information, right? It's some type of predictive information between, let's say, it's some type of mutual predictive information between a certain node Si and another node S0 at a certain time in the future. I cannot see you actually for some reason. So I was wondering if you kind of thought of this in this type of predictive information framework. And also as a question I was wondering is that, did you try to think of some kind of theory, like it's some type of predictive information decay that you're looking at? So did you try to, does this connect to some type of properties of the graph of the network that you're studying, like the eigenvalues of the graph, or any other type of properties? Did you like look into some theory as well?
I'm not sure if I understand the question. So in the end, what we hope to do is study causality, right? We want to understand how one thing causes another thing.
Yeah.
And information, to some extent, it can be purely correlational. And then it's not, let's say you have a system where one variable has a lot of information shared with another variable, but it's completely confounded. In that case, information theory is a bit difficult to study, but in the context that we use it here is that we have no confounding, like all the variables are known. So we can at least be sure about this driver node to be the one that shares the most information over time. So that one has to be causal. But it gets quickly really complicated with information theory in this polyadic setting, because you have all these, yeah, I have a lack of a good word, but you have these information diagrams you can show where you have synergetic information, which can be very important, and unique information and redundant information. So you can parse this space with various different questions that I think is getting into what you're referring to, that all gets different questions answered. But it's very difficult to analyze this in a general sense because of this space rapidly exploding. So in the end, we want to study causal interactions. And with complex systems, it's difficult because we have many interactions. Mm-hmm. And this is sort of a way in to reduce the complexity, at least to one node. But it's, of course, not the entire story. So yeah, ideally speaking, you want to do a full causal decomposition, and that's just very difficult.
I see. Okay. Okay. So maybe I can ask a second stupid question on the final, sorry, on the simulation that you're proposing at the end, really at the end. No, the one that you put on your GitHub. How big of a system can you simulate? Like if I would like to use this, these ones, yeah. How big are your system? Like.
It depends on your computer, I guess. I mean, I'm able to do this locally on my system. Easily, I can generate 20,000 nodes.
Okay. And in total, okay.
Yeah.
And then you can implement any rules, like it's.
Yeah.
Okay.
Yeah. So these are just examples. This is also simulated just for the nice visuals on lattice, but you can take any type of network structure.
Okay. Thanks.
Then we had Alexandru with the question.
Hi, very interesting talk. So I'm at the same institute as Peter. So I'm also interested in social networks, and from that perspective, people are interested also in ways to prevent or to manage the cascades, because cascades typically in that field are bad. And then, yeah. And people look at how to do it, or how to do it by interventions that are timely but also intelligent, because you don't want to start a reverse cascade, right? You don't, like instead of a market overheating, you cause the crash by stupid intervention. So have you looked? It may connect to your point about causality, because if you understand the causality very well, then probably have you looked via simulations or theory at interventions, or how that may postpone or manage the cascade, or stop it?
Yeah, so this actually ties in to, so my PhD is theoretically under the Dutch National Police. So they are actually also interested in trying to intervene on criminal networks. So what we believe this could be an interesting, this one could be an interesting way in, is that because this happens, it wonders like where you, at what time you intervene and on which nodes will have an effect on whether this tipping point can occur. So it could be that if you want to prevent this from happening, you should not target maybe the highest degree nodes, because that could be very costly. You could maybe already start intervening on these intermediately connected nodes to prevent this tipping from happening at all. Because one thing the Dutch National Police is facing is that they have like, I don't know, 20,000 police officers or so, but then they have 80,000 criminals running around on average. So they don't have the resources to intervene everywhere at the same time. So what you want is possibly a minimal necessity for intervention to have the desired outcome. And I'm not saying that this is like the holy grail of studying this system. This is a way of doing it. Because for instance, in control theory, what they do often is they identify a set of nodes that span all edges, for example, like a minimum dominating set, and then they apply a control signal. But what is often forgotten is that sometimes these control signals can require infinite amount of energy. So even though you can control the system to any space, it could be not feasible in practice. And what I would like to do here, at least I hope that we will work towards something that if we start intervening on this system and this control signal, does it actually lead to the desired outcome? Yeah.
Thank you.
I hope this answers your question.
Yeah, thank you. More or less, yeah.
We have a few more people lined up for questions, so let's move to Velimir Illich was next.
Hi, Casper. Hi, all. Thank you, Casper. It was excellent presentation. Really nice. I would have a question regarding these tipping points. When we take a look to similar concept that is mentioned here, phase transitions, they usually appears in thermodynamical limit. So in this context, it will be that complex system is of with infinite number of nodes, I guess. Did you consider the same in thermodynamic limit, or you consider finite?
This is all finite.
Finite, and
Yeah.
when you increase the size of the systems, what's going on with these effects? What is the role of the size of the system in the analysis?
Yeah, so I think I have to highlight one confusion. So I'm not sure if these are considered the phase transition in the traditional thermodynamic sense. Because in the thermodynamic sense, you would have a control parameter, right, that you are sweeping along, and then you get this phase transition. But this is more at a local scale, like non-equilibrium type, where we're looking out of equilibrium what the system is doing, and it's basically most of the time magnetized on one side of magnetization on either 1 or 0, and sometimes it happens to flip. Given enough temperature. So of course this is, I'm not sure what I'd set the temperature here, if it's more of a conceptual way of looking at it, but under the Curie temperature, and it's not too low, this will happen.
And how do we define this tipping point? What is this by definition?
Yeah, that's a good question, because I looked into this. So it depends on the literature that you're reading on how people define tipping points. So in the ecological sense, there's less of a mathematical defined definition of what a tipping point is. And most people refer to this book, but I forgot the author from like a few years ago that wrote a book under the name Tipping Points. And he basically refers to when a system changes to one regime rapidly to another regime. So in that context, we're looking at this. And in statistical physics sense, you can imagine that you have two energy wells with some boundary in the middle. And the tipping point occurs exactly when you're on this unstable point in the center. And it can go either way. And through like thermal noise, you can move around in the space. And sometimes it just happens to go into this different low energy state.
Okay, thank you very much.
No worries.
Okay, then we had some questions from Mark Golden, and then afterwards Johan.
Okay, thanks very much. Thanks very much, Casper, for a very clear talk. I think I'm the odd one out as the only experimentalist in this Zoom call. So I'm interested in sociology of electrons rather than people or Twitter feeds and things like that. So usually they're on the lattice, and we record two-dimensional maps of metal insulated transitions, for example, happening. Could be other people recording ferromagnetic domains changing. In our case, it's a strongly correlated electron system, so highly entangled system. And we get certain patterns out, and we're stuck as how to talk about them because there are no theoretical physics formulas for how these things work because they're too difficult for the current theoretical physics frameworks. So is it a completely stupid, or it probably is, you can just nod and I'll leave the call, stupid idea to go and look on your GitHub thing and try and just look to see what kind of patterns are appearing there and whether they look anything like the ones we see? Would there be any reason then to discuss saying, okay, this is what your thing shows for genetic thingamy or one of your other terms? Would that have any chance of helping us try and work out which of these many balanced parameters that are in the physics side are maybe leading this kind of transition just by looking at the similarity of these patterns?
So, I mean, the short answer would be maybe yes. So the advantage of information theory is that you abstract away from the underlying content, right? You just use distributions. And from that, you can have this language that exists outside the realm of reality to some extent. That's nice, but it's also, at some point, you need to talk about what's actually happening in the system. Because you can't just only stay in the bit space and saying, well, these bits interacting with each other and it doesn't really matter what they're doing. So information theory allows for a way to express things that are highly dissimilar in a similar space, but at some point you still have to interpret it in reality. And that can be simple, but can still also be very hard to do. I mean, if you have a 5-way interaction in some bit space, it's still very hard to interpret this.
Okay,
So
well, there could be cases where you've reduced the, let's say, rather than 5-way, you only have 3-way, and there'll be some next nearest neighbor term that leads to this pattern more often than that one, and then we could go and search in our parameter space with our friendly theoreticians to see if we can find an analog of that.
Yeah, you could. Yeah, I think so. It would be interesting at least.
Yeah. Okay. Thanks very much.
No worries.
We had Johan.
Yes, thank you. Thank you very much for your nice talk. I enjoyed it a lot. I have a question about also another analogy. Did you think of having an analogy of your information transfer with, say, power grid networks where you have currents flowing, and, for example, you could have some synchronization feature over there? Is there a relation between this?
I'm not sure I understand the question.
Now, if you would have, say, you have your network, but you could have some Kuramoto model defined on the network, and you have all these frequencies, and you can also think of it as a kind of a transformation. I think it's a transformation transfer from one node to another node. And
we think the collective is called information flows because there's actually metrics that are called information transfer entropy, for instance, and information transfer. It gets a bit difficult, but I just call it information flows as a general encapsulating term.
Okay, but you never try to have, say, a concrete, very simple dynamics going on, and then to see if you can still apply this info, or do you know if it's possible at all to have then some information description like you have?
Well, so in this example, this is by far maybe one of the simplest cases you can have. It's a simple random bit that the other elements just copy.
Yeah.
In the end, what you need for applying these methods are probability distributions. And they can be generated through a deterministic process if you just pin it in a certain way where you can generate distributions. They could be totally deterministic if you want. So I'm still not quite sure on what you're asking. So if I answer your question in a general sense, yes, you can apply these methods to something like, let's say, a Kuramoto model or equations dictating electrical transfer or something like this. It just kind of, then the trick becomes on how you represent the data.
Okay.
Because it's like, to some extent, if your system always does the same thing and you're only looking at one time step ahead, and for every state in the system is the same, your entropy will be 0. So your conditional entropy will also be 0.
Yeah. Okay. Yeah. Thank you.
Yeah.
Okay. Are there any other questions for Casper at this moment? If not, then I think we can thank Casper again for the very nice talk and extended Q&A session, which was also quite interesting. And thanks very much for coming, everybody.